And there are three basic problems in HMMs. Okay, so given observation sequence X and with the state sequence Z and the parameter theta. So first one, evaluation problem. So when we have an HMM, then the given a sequence X, then we wanna evaluate the likelihood of this sequence. So P of X. Okay, so P of X is the same as P of X given theta because, as I said, the theta is the parameters. Okay. So we're going to talk about the forward algorithm or backward algorithm. Okay. And the second one is decoding a problem or finding an optimal state sequence. Okay, so given X, then we want to find the best hidden sequence, Z. Okay, so speech recognition system is nothing but this decoding problem in the HMM. Okay, so given all the observations, audio signals, then we want to find the best sequence of hidden states. So the hidden states would be like the phonemes. Okay, so the sequence of phonemes will define the words and the sentence. And we will talk about Viterbi algorithm. And then the last one is a learning problem. So we have to estimate the parameters of HMM. Okay, so we have theta. Theta includes pi and a and the phi. Okay, so we want to update this parameter to maximize the likelihood. Okay, so this is evaluation, and so we just calculate the likelihood, and to learn we maximize the likelihood. So we updated this theta to maximize the likelihood, and we'll talk about bound-Walsh algorithm, which is a special case of EM algorithm, and the bound-Walsh is for the discrete observation, and for continuous observation we will use EM algorithm. Okay, first, evaluation. So as I said, we want to compute the likelihood of an observation sequence. Okay, this one is what we want. And then with this hidden latent variable, if we marginalize, then it's exactly the same as P of X. And then we can decompose this one. Okay, so as I said, for simplicity, we don't put this theta in equations. Okay, but there is a theta everywhere. And then we have a P of Z. Okay, so P of Z can be rewritten by this pi and P of Z sub n given G sub n minus 1. And then P of X given Z can be decomposed like this. Okay, and since we have k states with n time steps, we have to calculate k to the power of n computations, which is infeasible. Okay, so we're gonna use dynamic programming. So efficient implementation is possible with the forward procedure. So we use dynamic programming in the next slide. For all the problems, so we will define some kind of functions. So for the first problem, we defined alpha. Alpha is the probability of the observations from 1 to n, and the state at n is k. So this is alpha. Again, alpha is the probability of this subsequence, and the current state is k. Okay, and then a sub ij is the probability from state I to j. It is a transition probability. And the b sub I of xn is the p of xn given g sub n, which is emission probability. Okay, and then alpha can be obtained as follows. First, we initialize alpha 1. So alpha 1 is actually p of x1, z1 is k. Okay, so this one can be decomposed in this way. This one is p of x1 given z1, and p z1 is k. So that's what this is. And then this one goes to this one directly, and then this one is actually emission probability. So this is the initialization of alpha. And then we're going to use this induction. Alpha n plus 1 of k is this in this graph, which means probability of x1 to xn plus 1 and the z n plus 1 is k. So this is alpha n plus 1. So we have to calculate the probability at state k. So we have a probability of all the states at time n as alpha n of I. So from here, from the one state, we can multiply the transition probability to move to the state k, like this. And then at the time n plus 1, we have to calculate the emission probability. So that is alpha sub n plus 1 of k. Okay. Again, we have alpha sub n of I. Okay, this is induction. So we assume that this is given, and then this is given, and then this is given. So we assume that the HMM is already trained. So all the parameters are set. So A and B, these are given. And from this one, we multiply the transition probability and the sum. So from all the previous states, we can move to state K. Okay, then we can sum all the probability, and then we calculate the emission probability. This is alpha sub n plus 1 of K. And then finally, after all this induction, then finally P of X is sum of alpha capital N of K. So at the end of this sequence, okay, so we have this sequence. This is N is 1 and N is N. So at the last time step, we have K states. And then for each state, we have this alpha value. And we don't know which state will be the right state. So we have a probability for each state. So we have to sum all this probability to have a P of X. I mean, we have a state. From state, we have an observations, right? And then when we have a final observation, xn, and we don't know which state generates this xn. So there's probability that the first state can generate xn, and the second state can generate xn, the third and the last state can generate xn. So we have to sum all this probability to calculate P of X. Okay, so this one is feasible. We can calculate this one with k-squared times n operations. So for evaluation, forward procedure is enough. We don't need backward procedure. Okay, so if it is only for evaluation problem, then the forward procedure is enough. So with the forward procedure, we could calculate the likelihood of P of X. That's it. But we need backward procedure. Okay, so backward procedure can calculate the likelihood too. Okay, either way would be fine. So forward procedure or backward procedure, either way would be fine to calculate the likelihood. But in the decoding problem and in the learning problem, we need both. We need alpha and the beta. Okay, so let's define beta in this way. Beta is probability of a subsequence from n plus 1 to n, and the Zn is k. So this is the beta, and the A and the B are the same as before. And we can define this beta with this induction as we did for alpha. So initially, we can define beta n of k is 1. So look at this one. Beta n, if it is n, then the observation goes from n plus 1. So if it's n, then the observation goes from xn plus 1, which is not there. Okay, so we just initialize beta n of k to 1. And by induction, as you can see here, we can define beta of k in this way. In beta n, we don't have xn here. Okay, so from here, we multiply this emission probability of xn plus 1. Okay, so now we have xn. So for this one, we have xn plus 1. Emission probability is here. And then we have a transition probability, so that we have a beta n. So it's the opposite of alpha. Okay, and the termination is simple. P of X is the sum of beta k, and emission probability. Again, beta 1k does not have x1. Beta 1k is actually p of x2 to xn, and z1 is k. So we don't have x1 here, so we need emission probability x1 from k. So we have to sum them up. So now we have a p of x. Okay, again, as I said, backward procedure is enough to calculate the likelihood, or for the procedure is enough too. But we need both for the second and the third problems. And decoding. So decoding is something like a speech recognition system. So when we have an observations, what is the best sequence? So we want to find the optimal sequence z, and this z should be the best state sequence path, not the concatenation of best state at the current time. Okay, so that's the difference. We'll see that. Okay, and then z maximizes p of z given x. So when we have an x, then when we calculate the p of z, then it should be maximum. That's what we want as a z. And then as we did, we define another function, gamma. Gamma sub n of k is p of z sub n is k, and x is given. Okay, so when x is given, what is the probability of current state k? Okay, this one can be rewritten in this way with the base rule. Okay, and then we have a sum here. So I think this is simple. Okay, then consider that alpha is defined in this way and the beta is in this way. Okay, so alpha goes from 1 to n, and beta goes from n plus 1 to capital N, and both have the same kind of state. Okay, then this one, p of x, z sub n, can be rewritten in this way, alpha times beta. Okay, so this one and this one, there is no overlap. Okay, so we can multiply alpha and beta in this way, and then we are at the same state. That's good. And then we have to sum to normalize. This is gamma. Okay, so let's look at this gamma again. So gamma is the probability of a current state k given x. So we have a state, we have many states, and when we unfold, then we have this sequence of states, and then we have an observations for each time step. Okay, so given all these x, then at time step n, what is the best state? So if we maximize this one, then we can find the best state, z sub n star. Again, z sub n star is the best state at the current time step n, given all the x. Okay, then how about concatenating g sub 1 star, g sub 2 star, g sub n star? How about this one? Unfortunately, this is not the best path. At the current time step n, this z sub n star would be the best state for that time step. Okay, not considering all the other kind of states. But when we consider all of them at the same time, then this concatenation would not be the best path. Okay, for example, if z sub 2 star and z sub 3 star, so this one is at the state 2 and this one is at the state 7, okay? But if the transition probability between 2 and 7 is 0, then we cannot move from here to here. Even though z2 star is 2, which means at time 2, the best state is 2. At time 3, best state is 7, but there is no transition between 2 and 7, which means this cannot be the path, okay? So it's kind of greedy kind of algorithm. So we find the best state at the current time step. For every current time step, we find the best state. But when we concatenate all of them, something it could be, but it may not be the best path. Okay, so let's talk about the Viterbi algorithm to get the best path. Okay, now we want to define another function, delta. Delta is the maximum probability of this hidden state, and the time n, the state should be k, and we have n subsequence. Again, this is the highest probability of a state sequence path up to n, where the state is k. Okay. So with induction, delta n plus 1k is defined by this. So from here, and we multiply this transition probability. So in the next time step, we are at the state k. So this means p of z1 to zn. Zn is I, and zn plus 1 is k, right? And then we have x1 to xn plus 1 because we have emission probability here. So we can have state I and we can have state j for time n and time n plus 1, but we check the best I. So it is actually delta n plus 1 of k. Okay, and then we need to keep track of the state, then maximize this one. I mean, when we just calculate the delta, okay, then we can calculate the probability of the best path. But what we want is best path itself. So we want to keep this best state. So we define this psi. And psi is the best state considering this delta. Okay, so psi n plus 1 of k means this. For example, psi 5 of 1 is 3, which means at time step 5, if we are at state 1, then probably the most likely this one, the state 1, is from state 3 from the previous time step. Okay, so at time 5, state 1 is from state 3, most likely. Okay, so if we are at a certain state at the current time, then we know what is the best state in the previous state. That's what this psi means. Okay, again, delta is the best probability of all the hidden states when we are at state k at time n. Okay, and then psi defining the best hidden state in the previous time step. Okay, so we can run this Viterbi algorithm with this recursion. Okay, so initially delta 1 of k is this. So when we are at the first time step, this is the probability of first time step, and this one is emission probability. So that is a delta, okay, delta 1. And psi 1, because there is no previous state, so it's just a 0. And recursively, we can learn, we can update this delta and psi. So these equations are from the previous slide. And then at the end of this recursion, then we can calculate the probability, delta. So this one is the probability of the best state sequence path. So when we have the best state, sequence, state sequence, then this is probability. Okay. And this one is the last state of the best sequence. And then how can we find the best path? So best path can be retrieved by this backtracking. So the last time step, this is the best state, okay? And then psi n z sub n star will give us zn minus 1 star, okay? So from the last time step, we can check the best state of the previous time step. And then recursively, by backtracking, we can find all the path. So z1 star. Okay. So this is similar to the forward procedure, but in this, we have just the maximum. So in the forward procedure, we have to calculate the probability. So we have to sum all the possible probabilities. But in the decoding, we just find the best path. That's what decoding does. And finally, we have to talk about the learning. So in the problem 1 and 2, we have a trained HMM, and then we can calculate the likelihood and we can decode our observations. Now, finally, we have to learn this HMM. So learning is to update the parameter theta. Theta includes pi and a and phi. So pi defines the probability of the state at the first time step. And the a is the transition probability, and the phi defines the emission probability. So we use the b for the emission probability. So we are going to update these parameters to maximize the likelihood. Okay, it can be done by the Baum-Weiss algorithm. And again, we define another function, psi. And psi sub n of I, j is probability of, like this. At time n, the state is I, and at time n plus 1, state is j, given the old observation. So which means it is the probability of being state I at time n, the state j at time n plus 1, as you can see in this figure. So we can have some path, but at time n, we are at state I, and at time n plus 1, we are at j. And between these two, we have a transition probability and emission probability. So again, if we write this equation again, and we apply the base rule, so x is here, and then we divide this by this one, okay? And then if we look at this one, so at the end, we are at I, and at n plus 1, we are at j. And we have all the observations, so which means it can be rewritten by this alpha and beta. So alpha I can define all this path, and the emission of n, and the beta n plus 1 is defining all the paths without emission at n plus 1. So we need emission here, and then transition between I and j. So that's what this is. Okay, so from this alpha, we have some path, but at end, it should be I, the state should be I, okay? And with beta, we can have some path, but at time n plus 1, the state should be j. And then we have a transition between I and j, and we have emission probability at j, from j for xn plus 1. And then we have to normalize, okay? So if you look at this gamma, psi, and the gamma, the difference is just the j, right? So if we just marginalize psi, then we can get gamma. Okay, that's one relationship between the gamma and the psi. To drive the update rules, we can check some equations first. So we're going to take the sum of gamma and psi over the time n. First of all, we have equations for gamma and psi here. So gamma is the probability of current state given observations, and the psi is the current state and the next state given the observations. And when we take the sum of this gamma, then it is expected number of transitions from state I, or simply it is expected number of paths going through state I. And when we take a sum of this psi, then it is expected number of transitions from state I to state j. Okay, so using this above a formula, we can obtain the update rule for the parameters, assuming that observations are discrete. So we are talking about discrete HMMs. Okay, so we have three parameters, pi, and the transition probability A, and the emission probability B. So the first, pi is the probability of the state for the first time step, and that is exactly the same as gamma sub 1 of k. So if you look at this equation again, gamma 1k is actually p, z 1 is k given x. So this one is pi of k. And transition probability, we can calculate the ratio of these two terms. First, this one, the sum of psi is the expected number of transitions from state I to j, and sum of gamma I is a transition from state I. So basically this ratio is corresponding to the transition probability. And the third, the emission probability. So since we are assuming that the observations are discrete, so this emission probability can be represented as a matrix. So when we have a k state and when we have m observations, then we have a k by m matrix. And each cell can be estimated by this ratio. So here we have the expected number of transitions from state I, and this one is almost the same as this one except this condition. So this one says the expected number of transitions from state I, and the current observation is m. So this one is normalizing term, and this one is the expected number of transitions from I, and the observation is m. So that is actually emission probability. Okay, then in the previous slide we talked about the discrete HMMs. So the latent variable is always discrete, but discrete HMM means observations are discrete. But what about the continuous observations, continuous values for the observations? So as I said in the previous slide, emission probability can be estimated by this ratio. Okay, and then this is a matrix. But for continuous values, this is not kind of available. So we have to assume some parametric model. So the most common form of this probability is Gaussian mixed model. If you want, you can have a simple Gaussian, but most of the time, Gaussian mixed model is more popular. And the emission probability can be modeled by this mix of Gaussians. Okay, and each emission probability has a G Gaussian component. Okay, so for each state we have a G Gaussian component. So when we have 3 states and each state has 5 Gaussian components, then basically we have 15 Gaussian functions. And then for the continuous observations, this gamma should be generalized into a gamma of kg. So in this case, this term means the probability of the state k, but this term means the probability of state k and component g, because in each state we have a g component, so we need the index for the component, Gaussian component. So basically this one is the probability of being state k at time n with the g's component for the observation xn. So the estimation is similar to the discrete HMMs, but it's a little it's kind of extension of the previous one. So first of all, we have the same kind of term as the discrete HMM. So this one is about the probability that the current state is k, and this term is I think you're familiar with these terms from the EM algorithm for GMM. So this term means when we are at the state k, then which component this specific observation belongs to. So that is what this term means. And then since we are assuming the Gaussian mixed model for this emission probability, so we need some parameters for the mix of Gaussians. Okay, so this is the coefficient for each Gaussian component, and this one is a mean, and this one is covariance. So this term means that among all the possible components, then what is a ratio of this specific component g? Okay, so here we have a sum of all the components, and then here we have just the g. And then mu and the sigma, these parameters are exactly the same as EM algorithm for Gaussian mixed model. So we just update these parameters. Okay, and simply these update rules are based on the EM algorithm. So if you look at these terms, okay, observation sequence X as an observed data and the state sequence Z as an hidden or missing data, then the P of X is a likelihood of incomplete data, and P of X, Z is a complete likelihood. Okay, so this is exactly how we handle all these likelihood in the EM algorithm. Okay, and finally, I want to mention a couple of things about HMM. Okay, so first, in real problem like a speech recognition system, and true phonemes are hidden variables, Z sub n. and then the observations are acoustic features. So conceptually, we assume that the Z sub n, the phonemes, can generate acoustic features with GMM. That's conceptual kind of idea, but instead of using this emission probability directly, we actually train this recognition model or discriminative models. Okay, so because what we have is observations. Given these observations, what kind of phonemes this observation acoustic features belong to? So we recognize the phonemes first. So usually we can use neural networks since 2010s. Okay, and then we apply the Bayes rule to reconstruct this emission probability. So this one is emission probability, and this one is recognition model. And when we multiply this P of xn and the P zn, if we multiply these terms to this one, then we can reconstruct this emission probability. But usually in the real speech recognition systems, we don't actually estimate these things. We just use constant value. We just estimate. Okay. And recently, in many sequential data modeling tasks, deep learning has been actively replacing HMMs. So there are many neural network architectures like recurrent neural networks, convolutional neural networks, or transformer, and etc. etc. There are many neural networks, and they have a continuous hidden states. It's more powerful, so they have more expression power. Okay, but still, even in deep learning era, we can use a lot of dynamic programming we learned from the HMM. So for the procedure and the Viterbi algorithms, we talked about the dynamic programs. So I hope you learn these dynamic programs, and then you can apply these things to deep learning later. Thank you.